This podcast is on energy, enthalpy, and the heat of chemical reactions, and it is in actual fact another application of stoichiometry. Energy. Energy is the capacity to do work or to transfer heat, and in chemistry we'll focus on the transfer of heat or the enthalpy of the system. As you may know, energy comes in two forms, kinetic and potential. Well, the energy stored in the chemical bonds is of interest to the chemist. Some definitions. Temperature is the measure of the random motion of the components of a substance. It's on an arbitrary scale we call degrees, and temperature is not heat. Heat, or enthalpy, is the flow of the energy between substances of different temperatures, always from a higher temperature to a lower one. Enthalpy is a change that we can measure. It is, in fact, the difference between the heat content of the products and the heat content of the reactants, or where you got to minus where you came from. This enthalpy change is called the enthalpy of reaction, or the heat of reaction, and is sometimes given the symbol delta H. Consider the equation for the production of water. This equation tells us that 483.6 kilojoules of energy are released, notice the negative sign, to the surroundings when 2 moles of water is formed and the reaction vessel would feel hot to the touch. This is called a thermochemical equation. Now, calorimetry is the method chemists use to measure and to calculate heat flow, or enthalpy, and it's based on a variety of things, but primarily the identity of the substance, how much of that substance you have, and the temperature change. So in the calculation we have Q, and Q stands for the quantity of heat. The M is the mass of the substance, C is the specific heat capacity of the substance that is absorbing the heat, and finally the delta T, and we end up with the equation Q equals MC delta T, where delta T is temperature final minus temperature initial. The common way it's done in chemistry class is to use a coffee cup calorimeter, and that's a couple of styrofoam cups. You may or may not have a styrofoam cover. Thermometers have been replaced by temperature probes with the Vernier LabQuest, and usually they're a resistor. Sometimes they're made out of metal, sometimes they're glass. So, sample calculation. Calculate the heat involved when 30-gram sample of silver cools from 100 to 25. The specific heat capacity of silver is 0.235 joules per gram degree C. Well, Q equals MC delta T, and so we end up substituting, doing the calculation, and we determine that the value is negative 528.75 joules. The negative sign means that the heat was lost to the surroundings, and if you do temperature final minus temperature initial, you will notice we have 25 minus 100, or negative 75 is our delta T. That indicates that the heat was lost to the surroundings, and we have words for whether or not heat is lost to the surroundings or gained from. If it is endothermic, that means that energy flows into the system as the reaction proceeds. That is, that the system gains Q, gains heat, so the surroundings have lost them. The opposite is when the reaction releases its energy, and the energy flows out of the system, and so the Q for the system is negative, and the Q for the surroundings is therefore positive. And they have to equal each other because heat lost equals heat gained. We have the law of conservation of energy here. No energy is destroyed. It is only transferred. Graphically, you can look at them, and you can see that we have here a system that has the reactants on the left, the products on the right, and when the heat flows, we have a difference between them, and that difference is delta H. And if the energy of the products is greater than that of the reactants, we say that the delta H is going to be positive, and the reaction is endothermic. The reverse, of course, is an exothermic reaction. And what we have here is reactants go to products plus energy. The curve then goes down. You have the reactants again on the left and the products on the right. And as you look at the differences in the energy, you will see that we have the reactants in green, products in red, and then the difference between them is going to be the delta H, and that delta H this time is negative because this happens to be exothermic. Delta H being negative means it's exothermic. Think of burning a match. Here you have the system, it's the reactants, and that is at a certain energy level. When you strike it, it burns, and the energy is released to the surroundings as heat, and the delta H for that system is negative. Okay. Well, heat's a stoichiometric quantity. The more moles that react, the more heat's involved. And we use what's known as the molar heat of reaction, delta H for reaction, in our calculations, where Q, the quantity of heat involved, is equal to the number of moles times the delta H for the process we're looking at. So, if you look at an example, how much heat is liberated by the complete combustion of 9 grams of glucose at 25? There's the thermochemical equation. Glucose plus 6 oxygen makes 6 carbon dioxide and 6 waters, and the delta H is negative 2820 kilojoules. What that means is that the heat is released and that the molar enthalpy of combustion of glucose, delta H combustion, is negative 2820 kilojoules per mole of glucose that burns. So the way that we do this is you take your 9 grams of glucose and convert it into moles, and you end up with 0.05 or a 20th of a mole. You then multiply that by the molar heat of combustion of glucose and determine that our Q is going to be negative 141 kilojoules, which means that the heat liberated is 141 kilojoules. The surroundings absorb that 141 kilojoules, and we can actually continue with another part of the problem. What will the temperature change and final temperature of 500 grams of water, initially at 25 degrees C, be if all the heat from the burning the 9 grams of glucose is absorbed by the water? It's the same equation. Q is equal to mc delta T, but now we have the Q. The Q is 141 kilojoules, or 141,000 joules. And that is equal to the m times the C times the delta T. If we substitute in our values and solve, we end up finding that the delta T is 67.4 degrees C, and since we initially began at 25, our water will get up to 92.5 degrees C. And those are some examples of heat and calorimetry and stoichiometry.